In the last two classes, we have discussed about the radial basis function neural network, and we have also discussed about if I compare the radial basis function neural network with multilayer perceptron, what is the advantage and disadvantage of the radial basis function neural network with respect to the multilayer perceptron. So, we have said that in case of radial basis function neural network, the network consists of three different layers. One of the layer was which is present in all types of neural network, that is the input layer, which basically accepts the input feature vector and forwards that input feature vector to the layers above it. In case of RBF neural network, we have one hidden layer and one output layer. The neurons in the output layer basically determines that what is the class belongingness of the input feature vector, and the function of the neurons in the hidden layer is to compute a radial basis functional value, and through this radial basis function, what we effectively do is we map the input feature vector from its original dimension to a higher dimensional space through a nonlinear mapping or a nonlinear transformation. And this nonlinear mapping is actually done by the set of radial basis functions. And the purpose why we perform this transformation, a nonlinear transformation from a lower dimensional space to a higher dimensional space, is that if you increase the dimensionality of the feature vectors, then the feature vectors belonging to different classes, if they are not linearly separable in a lower dimensional space, it becomes quite likely that they become linearly separable in higher dimensional space. So, that was the basic motivation that we have in case of radial basis function neural network. And as by increasing the dimension of the input feature vectors, we are increasing the possibility of linear separability. So, the output layer of the radial basis function neural network simply computes linear combination of the outputs of the middle layer nodes, and based on this linear combination of the output of the middle layer nodes, it decides to which class the input feature vector x should be classified. So, as a result, the output layer node that we have, I mean starting from the middle layer nodes to the output layer node, so that section of the radial basis function neural network is effectively a linear classifier. So, the advantage that we have in case of radial basis function neural network is that I know how many hidden layers I have to have, it is only one. In case of multilayer perceptron, I cannot easily decide that how many hidden layers I should have. Similarly, how many nodes per hidden layer in case of multilayer perceptron, that is also cannot be easily decided, whereas in case of RBF network, radial basis function neural network, I can set how many nodes in the hidden layer I need to have, because it is simply the dimensionality of the space to which I want to cast my input feature vectors. The other advantage is the interpretation of the functions of the hidden layer nodes, which is quite easy in case of RBF neural network, but the interpretation of the functionality of the nodes in the hidden layers is not that clear in case of multilayer perceptron. Also, the training in case of hidden layer is faster than the training in case of multilayer perceptron. The only disadvantage, apparent disadvantage of the RBF neural network is that the classification task in case of RBF neural network takes more time than the classification in case of multilayer perceptron. So, this is what we have discussed over last two classes. Today, we are going to discuss about another kind of classifier which is called a support vector machine. So, we will discuss today the classifier known as support vector machine or SVM. So, when we start our discussion on support vector machine, let us recapitulate one of the previous classifiers, the linear classifiers that we have discussed, that is a linear discriminant function. So, during our early one of the early lectures, we have said that if we have an input feature vector x and we define a linear discriminant function say g of x. So, for simplicity, let us consider that we are considering a two class problem. We have two classes, one is class C1 and the other one is class C2. So, we are talking about two class problems, class C1 and class C2. And an unknown feature vector say x is to be classified as either belonging to class C1 or belonging to class C2. And for doing this, when we talked about the linear discriminant function, we have defined a linear discriminant function say g of x, which was put in the form w transpose x plus b. Or maybe in the earlier lectures, we had put g of x as w transpose x plus w naught. It was something like this, where x is the input feature vector, w is the weight vector and w naught is a bias term. So, you find that this is a linear function. In a two dimensional space, if our feature vector is a two dimensional vector, then this linear equation represents a straight line. If our input feature vector is a three dimensional feature vector, then this linear equation, if I put this equal to 0, then I get a linear equation w transpose x plus b equal to 0. So, this linear equation in two dimension represents a straight line. This linear equation in three dimension, it represents a plane. Whereas, if I increase the dimension, where the dimensionality of the feature vector is more than 3, this linear equation actually represents what is called an hyperplane. And w is nothing but a vector which is perpendicular to that hyperplane. So, this vector w, it represents the orientation of the hyperplane in my d dimensional space, where d is the dimensionality of the feature vector. Whereas, this term b, or coming to the previous one, the term w naught, which is a constant, it represents what is the position of that hyperplane in my d dimensional space. So, the vector w represents the orientation of the hyperplane and the value b or w naught, it represents the position of that hyperplane in my d dimensional space. So, this b, term b, is usually known as a bias term, which is biasing the position of the hyperplane in the d dimensional space. Now, coming to our classification problem, for every feature vector x, I have to compute this linear function w transpose x plus b, and if this x lies on positive side of the hyperplane, then I will have g x, or let us take a specific vector say g x 1. This is a vector, a specific vector, the first vector, which will be equal to w transpose x 1 plus b. if this x 1 is on the positive side of the hyperplane, then I will have W transpose x 1 plus b, which will be equal to 0, which will be greater than 0. And if x 1 belongs to negative side of the hyperplane, then I will have W transpose x 1 plus b, which will be less than 0. And if x 1 lies on the hyperplane, then I will have W transpose x 1 plus b is equal to 0. So, this is a hyperplane which divides my d-dimensional space into two half spaces. In one of the half space, if I take a vector, then g of x for that particular vector x will be positive. If I take the vector x into the other half space, then g of x for that vector will be negative. And I can have my classification rule that if W transpose x 1 plus b is greater than 0, then I infer that this x 1 will be classified to class C 1, that is it belongs to class C 1, whereas if W transpose x 1 plus b is negative, then I can infer that this x 1 belongs to class C 2. So, this is my classification rule. So, what we said is initially we have to train this classifier, that means I have to find out what is this W vector W and what is this bias term B, so that this g x with that W, the trained value of W and trained value of B can be used as the classifier. So, for training we have used supervised learning. So, we have been given a large number of samples, some of the samples coming from class C 1 and some of the samples coming from class C 2. So, using these training samples, when I try to train the network, then training of the network was done in an iterative fashion. So, for every training sample belonging to class C 1, we started with an initial value of W and B, and for every training sample belonging to class C 1, we have tried to see that whether W transpose x plus b is greater than 0 or not, because we have taken a sample from class C 1. So, it has to be greater than 0. If it is not greater than 0, then we have modified W and B in such a way that the position of the hyperplane or as well as the orientation of the hyperplane is so modified that that particular x which is taken from class C 1 is moved to positive side of this hyperplane. Similarly, if I take a vector from class C 2, we have checked whether this W transpose x, where x is taken from class C 2, is negative or not. If it is not negative, then again we have modified W and B. So, there again we have tried to see that if this is negative or not. If it is not negative, then we have modified W and B in such a way that that particular x is moved to negative side of the hyperplane. So, this is what we have done in case of linear discriminator. And we have also said there that if a sample is just beyond this hyperplane W transpose x 1 plus b equal to 0, even then it might be correctly classified. But the classifier that I so obtain, so I can have a situation something like this. I have one feature vector, let us take two dimensional feature vectors something like this. So, these are the feature vectors which say belong to class C 1, and I can have a set of feature vectors something like this which belong to class C 2. This is my x 1 dimension if I have a two dimensional feature vector, and this is my x 2 dimension. So, these are the two components of the feature vector. Now, if I have a classifier or a hyperplane in 2 dimension, which is a straight line, as we said earlier, is something like this. And these are the feature vectors which are given for supervised learning. So, if I have a situation something like this, even here you find that this straight line in d dimension, it is a hyperplane, correctly classifies all these feature vectors which are given for training of the classifier. But whether this type of classifier is desirable, is it desirable? Obviously, a classifier of this nature is not desirable, because this classifier gives a large bias in favor of class C2, whereas it puts a penalty against class C1. The reason is this entire space from here to here, this is given to class C2, whereas the margin to class C1 is only this much. Rather than this classifier, I would prefer to have a classifier somewhere over here, so that the training vectors both from class C1 and class C2, they are equally apart from my classifier, or the plane separating these two different classes. And the support vector machine actually tries to find out a classifier which will be positioned in a form something like this. Okay. So, now let us see that how such a support vector machine can actually be designed. So, the basic aim of this support vector machine is, see, if I am standing on one side of the boundary, and if there is a possibility that I can cross the boundary on the other side, I will feel safer if my distance from the boundary is larger. If my distance from the boundary is very small, so this is my boundary and I am standing somewhere over here, then a little disturbance or a little noise can push me to the other side of the boundary, in which case I will be misclassified. But if I am standing somewhere over here, where this is my boundary surface, then the margin that I have is quite large, right. So, to push me to the other side of the boundary, to make me misclassified, there has to be a large disturbance. So, I feel that I am safer if my distance from the boundary is very large, okay, and I am not safe if my distance from the boundary is very small. So, this is the kind of situation that I have. So, what the support vector machine, the way the support vector machine tries to design the classifier is that it tries to maximize the distance of the separating boundary between the two classes by maximizing the distance of the separating plane from each of the feature vectors, whether the feature vector belongs to class C1 or the feature vector belongs to class C2. Okay. And out of this, when I talk about the support vectors, okay, right, I will come to that point a bit later. So, what I have is, suppose I have a vector x I, and if this vector x I belongs to class C1, then I will have W transpose x I plus B, it has to be greater than 0. This W transpose x I can also put in the form of a dot product W dot x I, because this operation is same as this operation, plus B, that has to be greater than 0. If this x I belongs to class C1. If x I belongs to class C2, then I have the situation W transpose x I plus B have to be less than 0 if x I belongs to class C2. So, here W transpose X I plus B will be positive, here W transpose X I plus B will be negative. Now, what I can do is, when I go for designing of the classifier, I know to which of the class the sample X I belongs. I know whether X I belongs to class C1 or X I belongs to class C2. So, along with every X I can assign a class belongingness. So, what I can put is, along with every X I can also give an Y I, mention an Y I, where this Y I can be either plus 1 or minus 1. So, if X I belong to class C1, the corresponding Y I will be positive. If X I belongs to class C2, the corresponding Y I will be negative. And if I feed the data in this form and I compute Y I into W transpose X I, W dot X I plus B, this will always be positive, irrespective of whether X I belongs to class C1 or X I belongs to class C2. Because if X I belongs to class C2, then W dot X I plus B is positive, Y I is also positive, which is specified. So, this product will be positive. If X I belongs to class C2, then W dot X I plus B will be negative, Y I is also minus 1. So, you take the product of these two, the product term will be positive. So, this is what I will have. And using this concept, I can go for the designing of the classifier. Okay. And once I get W and B, then for an unknown feature vector, say let us take an unknown feature vector P, this is an unknown vector. Which has to be classified. I have to put this unknown vector P into either C1 or C2 using the W and B that has been obtained after designing the classifier. So, once I do that, now I do not have any Y I, because P is unknown. So, I simply compute W dot P plus B, where W and B they have already been decided during the training process. So, if this W dot P plus B becomes greater than 0, I classify this P to belong to class C1. If this is less than 0, I classify P to class C2. So, this is the kind of situation that I have. And as I said that in case of support vector machine, my aim is that I want to maximize the distance of the hyperplane or the separating boundary from each of the feature vectors, so that every feature vector feels that they are safer so far as this classifier is concerned. Okay. And the distance, and to do that, we have made a modification in our classifier design, linear classifier design, when we talked earlier, that instead of considering W transpose X I plus B to be greater than 0 for correct classification, we have said that I want W transpose X I plus B should be greater than some gamma, where gamma we have said margin. And this margin is nothing but a measure of distance of X I from the separating plane. So, if I have an hyperplane whose equation is given by W dot X plus B is equal to 0, distance of a point X from this hyperplane is simply given by W dot X plus B upon mod of W. So, this is known from school level geometry. So, this is the distance of X, point X, from this hyperplane W dot X plus B equal to 0. And what we want is, we want that this has to be greater than or equal to some margin, say gamma. Okay. And my decision regarding the correct classification of the feature vectors is independent of scaling of vector w, because vector w simply tells me that what is the orientation of the plane. So, whatever scaling factor I apply to w, my decision remains the same. Okay. So, I can simply put that this w trans dot x plus b has to be greater than or equal to this into w. And by proper scaling, I can set that this is equal to 1. I can set this term equal to 1. This is simply a matter of scaling. In which case, for every vector, I have to have a situation that w dot x plus b has to be greater than or equal to 1 if x belongs to C1, it has to be less than or equal to minus 1 if x belongs to class C2. And now, for a vector xi, if I multiply by the corresponding yi during the learning process or training process, I will have a situation that yi into w dot xi plus b, this will always be greater than or equal to 1. And this equality, this yi into w dot xi plus b will be equal to 1 if xi is a support vector, and it will be greater than 1 if xi is not a support vector. So, then the question comes that what is my support vector then? So, to explain what is my support vector, I simply go to my two-dimensional example. So, I have two-dimensional vectors x1 and x2. I have a set of feature vectors from say class C1, which is like this. So, this is class C1, and I have a set of feature vectors coming from class C2. So, I put it of this form. So, these are the feature vectors which are coming from class C2. Now, you can find that I can easily find out that if I draw a straight line over here, if I draw another straight line over here, these are the feature vectors from the training vectors which are just on the boundary of the classes. So, any disturbance to the feature vectors will greatly affect this, it will greatly affect this, it will greatly affect this. But if this feature vector is slightly disturbed, my classification result is not going to vary that much. Okay. So, I have to put my classifier somewhere in the middle of these two, and this is a classifier which will be more reliable, or it is called more generalized, okay, where my risk of misclassification will be less. And you find that the position of this classifier or this hyperplane depends on the position of this feature vector, it depends on the position of this feature vector, it depends on the position of this feature vector. It does not depend upon the position of this feature vector. Even if I remove this feature vector from my training set, or even if I remove this feature vector from my training set, the position of the hyperplane remains the same. But if I remove this feature vector from my training set, the position of the hyperplane is going to be different. So, these are the feature vectors which are called support vectors. The other vectors are not support vectors. So, this support vector machine is again a linear machine whose design is greatly influenced by the positions of the support vectors. Its position is not that much influenced by the vectors, by the feature vectors which are not support vectors. So, that is why I said that from this that y I into w I dot x I plus b will be equal to 1 when I have, when this x I is a support vector. So, I have y I into w dot x I plus b, this will be equal to 1 if x I is a support vector. So, this equality holds only for the support vectors. And now, what I have to do is, if you look at this expression, that what I want to do is, because this w dot x I plus b is a measure of distance of point x I from the plane w dot x I plus b equal to 0. So, this is a factor which has to be, and I want to maximize this. So, this is a factor which has to be used for designing of my support vector machine. Okay. And here I said that I want that this distance, or over this distance, the margin has to be as maximum as possible, which can be done from this expression by minimization of mod of w, and at the same time by maximization of the bias b. So, when I try to get this support vector machine, I will try to minimize this w, and simultaneously I want to maximize this b. So, if I want to minimize this w, so this is this w or the weight vector that I want to minimize. So, the minimization of w is same as if I want to minimize a function of w, which is nothing but w transpose w or w dot w. These two are same operations. And for mathematical convenience, which will be clear later on, I just put a term half. So, half of w dot w that I want to minimize, and if I want to minimize this, the trivial value will obviously be w equal to 0, which is not the solution that I am looking for. So, for minimization of this, I have to look for what is the other constant that I have. My constant is that for support vectors, I have to have w transpose dot x I plus b, this into y I, that has to be equal to 1. So, this is my constant. So, I want to minimize w, or I want to minimize phi of w subject to the constraint that y I into w dot x I plus b has to be equal to 1. Or I can say that this has to be greater than or equal to 1. If x I is a support vector, then this has to be equal to 1. And because my support vector machine depends upon the support vectors, so I will not take this inequality, rather I will take this equality, that is y I into w dot x I plus b has to be equal to 1, that is the constant, and under this constant I have to minimize my weight vector w. So, because it is a constrained optimization problem, this problem can be converted to an unconstant optimization problem by using the Lagrangian multiplier. So, I can put a Lagrangian multiplier, I can define a Lagrangian of the form LWB, because as we said that I want to minimize w, I want to maximize b, will be half of w dot w minus sum of alpha I into y I into w dot x I plus b minus 1. Right? And I have to optimize this Lagrangian, where this alpha I is the Lagrangian multiplier. So, when I go for optimization of this Lagrangian from our school level mathematics, we know that this optimization has to be done by taking the derivative of the Lagrangian with respect to W and by taking the derivative of the Lagrangian with respect to B. So, if I take the derivative of this Lagrangian with respect to B, then what I have? So, what I want to compute is del L upon del B. This is what I want to compute and I have to equate this to 0. So, for doing this, let us try to expand this equation and let us see what is this expression. So, in the expanded form, I will have L W B is equal to half of W dot W minus sum of alpha I y I into W dot x I minus sum of alpha I y I B plus sum of alpha I. So, this is the expression or the expanded form I have. Clearly, if I take the derivative of this with respect to B, so I want to compute del L del B. So, this del L del B, obviously from here you find that this is independent of B, this is independent of B, this is also independent of B. So, the only term which involves B is this. So, del L del B will be simply minus alpha I y I, and that has to be equal to 0. So, I get one constant, that sum of alpha I y I, that has to be equal to 0 for I varying from 1 to say m, where m is the number of feature vectors which are given for designing the classifier. Okay. So, this is one of the constant that I have. Next, what I will do is, I will take the derivative of this Lagrangian L with respect to my weight vector W. So, again this is the same Lagrangian if I put in the expanded form, and if I take the derivative of this, let me rewrite this Lagrangian. So, L of W B is equal to half of W trans dot W minus sum of alpha I y I W dot x x I minus sum of alpha I y I B plus sum of alpha I. Each of these summations will be from I is equal to 1 to m if I have m number of feature vectors provided for designing the classifier. So, now if I take the derivative of this Lagrangian with respect to W, so what I will have is, I will have del L del W. So, when I take del L W, del L del W, this will simply be the derivative of this with respect to W is nothing but W, and derivative of this with respect to W is sum of alpha I y I x I. You find that this term is independent of W, this term is independent of W. So, derivative of these terms with respect to W will be equal to 0. And once I take this derivative, I have to take this, equate this derivative equal to 0, which gives me W is equal to sum of alpha I y I x I, where this I will be from 1 to m as m is the number of training samples. So, through this derivative process, so this is the w that I have, which is my weight vector. You find that this is not a dot product. So, this is y I into x I. X I is a vector, alpha I is a scalar, y I is also a scalar. So, this entire term is a vector. Okay. So, through this optimization of the Lagrangian, I have got two equations. One is this, sum of alpha I into y I for I is equal to 1 to m is equal to 0, and I have this expression for my weight vector w, where w is equal to alpha I y I x I, where x I is the ith training feature vector for I varying from 1 to m. So, these are the two expressions. Now, if I put this expression in my original expression of the Lagrangian, then let us see what we have. So, by putting this in my original Lagrangian expression, as we said that the Lagrangian was in the expanded form, it was L is equal to half w dot w minus summation of alpha I y I b minus sum of alpha I y I w dot x I plus sum of alpha I. Okay. So, in the expanded form, which we said earlier, this is half of w dot w minus alpha I y I w dot x I, that is this term, minus sum of alpha I y I b, which is this term, plus sum of alpha I. Now, over here, this alpha I y I, this sum was equal to 0. So, this term simply gets cancelled. So, the expression I have is L is equal to half of w dot w minus this plus sum of alpha I. And if I put this value of w into this expression, then what I will have is this will be simply half of summation alpha I, because I have the term w dot w, dot product of the weight vector with itself. So, I have to have two different subscripts over here, one I, the other one I will put as j. So, this will simply be alpha I alpha j y I y j into x I dot x j. So, this is a dot product minus this will simply be again w dot x I, and the w is sum of alpha I y I x I. So, this will simply be minus summation of alpha I alpha j y I y j into x I dot x j plus sum of alpha I, and which is nothing but, you find that this minus this term and this term they are same. So, this will be simply sum of alpha I for I varying from 1 to m minus half of sum of alpha I alpha j y I y j, sorry, this will be j into x I, okay, x j dot x I, which is same as x I dot x j. So, it does not matter. So, I have the Lagrangian expression which is this. So, for designing, what I have to do is I have to maximize this Lagrangian with different values of alpha, which are my Lagrangian multipliers. And Lagrangian multipliers are always positive. So, I have one constant that alpha I always have to be greater than or equal to 0, and the other constants that we have is from here that sum of alpha I y I varying from 1 to n that have to be equal to 0. So, I have to find out such Lagrangian multipliers which maximizes this expression, this Lagrangian expression. And when you try to maximize this Lagrangian expression, it is quite likely that sum of the Lagrangians will be equal to 0, few of the Lagrangian multipliers will be equal to 0, and few of the Lagrangian multipliers value will be very high. So, if a Lagrangian multiplier and alpha I is equal to 0, that indicates that the corresponding training feature vector x I is not a support vector. If a particular alpha I is very high, that indicates that the corresponding feature vector x I has a high influence over the position of my decision surface or the hyperplane. The other possibility is of course there, if I get an alpha I which is extraordinarily high, I can infer that the corresponding feature vector which is given, it is a spurious point which might have occurred due to noise, it is a disturbed point, okay, or it is an outlier. So, all these different types of interpretations that I can have over alpha I. So, obviously, if alpha I equal to 0, the corresponding x I is not a support vector. So, it does not influence the position of the hyperplane. So, what I have to do is, I have to use these alpha i's, or I have to use with these alpha i's the value of w that I compute, which is given by this w goes into my decision making process. So, as a result, my classification decision will be like this, that what I will compute is for an unknown z, if I have a feature vector z which is unknown, the classification decision, if I say that the decision is dz, dz will be simply I have to compute alpha j y j into x j times z, because you find that my w is nothing but alpha I y I x I. Okay. And what I have to compute is this w dot z, right. So, that is what I am doing, alpha j, simply this subscript I is replaced by subscript j. So, it does not matter. So, I have to compute alpha j y j x j dot z, take the summation over j is equal to 1 to m plus b, and only the sign of this is important for classification. I don't need what is the value of this function, I simply need the sign of this function. So, sign of this is important for classification. If the sign is positive, then this z will be classified to class C1. If the sign is negative, then this z will be classified to class C2. So, now if I write the steps of the support vector machine design, the steps of the support vector machine design will be something like this. Yeah. So, one more point that I should mention over here, as we have done in case of radial basis function, if the original set of feature vectors in a lower dimensional space is not linearly separable, then I cannot have the support vector machine, because it assumes that the samples are linearly separable. So, if they are not linearly separable in lower dimensional space, I have to cast these feature vectors into higher dimensional space by using functions like radial basis functions, which are called kernel functions. So, once I cast them into higher dimensional space, then by taking the samples in the higher dimensional space, I can try to design the support vector machine. And then again for classification, like when you have classified this feature vector z, before classification I have to cast that into same higher dimensional space, and after casting that into higher dimensional space, I have to compute this term in the higher dimensional space. And then I can compare the sign of this term. If the sign is positive, then it will be in class C1. If the sign is negative, it will belong to class C2. So, I need two terms. One is W, which has been obtained by optimization as this particular expression. The other one, I need what will be the value of B. Okay. So, the value of B I can compute as this is the margin, B will be half of minimum of sum of alpha I, y I, I will put it as x I dot x j, okay, for all I for which y I is equal to plus 1, plus I have to have maximum of sum of alpha I y I into x I dot x j for all I where y I is equal to minus 1. So, that is how I get the value of B, and this W and this B goes in this expression for classification of an unknown feature vector Z. Okay. So, this is how our support vector machine works, and as I said before that this support vector machine is again nothing but a linear machine. Only thing is it helps in placing the separating boundary between the two classes, or it simply states where my hyperplane should be placed, so that the classifier that I get, that is more robust or more generalized. Now, instead of a two class problem, if I have a multi class problem, then I have to have multiple number of support vector machines. So, I have to have one support vector machine which tells me whether a sample belongs to class C1 or it does not belong to class C1. Then I have to have a support vector machine which tells me whether a sample belongs to class C2 or it does not belong to class C2. So, I will have multiple number of support vector machines for a multi-class problem. And it can be shown that if I have n number of classes, then what I need is n minus 1 number of support vector machines, like I have to have n minus 1 number of linear classifiers. Okay. So, with this I stop here today. Thank you very much.